I'm Nat, and today we are now going to do Deriving Formulas 7, the summation formulas. And now I'm going to teach you how to derive them. So let's start with the simple linear summation. 1 plus 2 plus dot 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 plus n. This has been proved by Gauss when he was 9 in a possibly interesting story about a teacher asking him to solve all the numbers from 1 to 100. You might have heard of this method already, so we're just going to review it here. So what we're now going to do is that we're now going to split the numbers up into two groups. One with n over 2 at the start and one with n at the end. Great. So this means we will split the numbers into two groups and we split them into parts. So 1 plus n, 2 plus n plus 1, and n over 2 and n over 2 plus 1 all sum to the same sum, right? N plus 1. And there are n over 2 n plus 1s, so we can write this as n over 2 times n plus 1 equals to n plus 1 over 2. This is probably how you learn how to derive it, so let's talk about another method. This is the method that I was taught in further math, and I'm going to tell it to all of you right now. So we now use the telescoping sum. This telescoping sum, k plus 1 squared minus k squared is n squared plus 2n. So we expand the left-hand side to become 2k plus 1. And you get n squared plus 2n. So then we split the summation because summation is additive and is also scalar multiplicative, meaning that when you multiply the expression inside by a scalar, the whole sum is multiplied by a scalar. Makes kind of sense, right? So say you had this great big sum, and then you have two of those great big sums, then you have twice that great big sum, and you don't have to do any math to prove it, because I just proved it in front of you. Great. And now we are now going to use the identity. K equals to 1, summation 1 to n is n. This might seem a bit obvious, right? Actually, it's quite straightforward, and I'll prove it to you. So let's say you have a row of n dots. So you can count all these dots as 1, 1, 1, 1, 1, 1, 1. But since it's a linear function, it's n. There are n dots in a row. There, I just proved it. Okay, so we're now going to expand the expression and simplify it to get 2 summation k plus n equals to n squared plus 2n. Then we're going to move the n to the other side to get n squared plus n. Continuing on from there, we now have k equals to n squared over 2 plus n over 2. Or in your period of simplifying equations, n plus 1 over 2. That alternative method might sound a bit long, but we're going to see how we are going to derive the other summation formulas. Let's start with the quadratic one. It's by far the next simplest case just after the linear. And once again, we're going to use a telescopic sum. This time, this summation is a bit more complicated because, well, we're doing a quadratic summation. We're not linear anymore. This is not an easy mode. Moving on, we expand the left-hand side again, and then we expand it using the summation identities. Then we use the summation of k and the summation of 1 we now have to add on the left-hand side, move them over, but before we move them over, let's just first simplify the terms on the left-hand side to get 3n squared over 2 plus 5n over 2. But how do we get rid of those pesky terms on the left? Simple, we just move them over to the right-hand side. And this means that we can simplify our equation to summation of k squared to be n cubed over 3 plus n squared over 2 plus n over 6. Or again, in your period of simplifying equations, use Wolfram alpha. Or, let me give you a better alternative, just memorize the factorizations of expressions. Or use the window method described in my A-level mathematics video 1. Let's do a cubic this time. What's the cubic summation? Well, we're about to find out because this result's going to be very, very surprising. Once again, we use the telescoping sum, and now the telescoping sum is much, much more complicated with 4 terms now instead of 2. Again, this is not an easy mode. Great. So now we expand out the left-hand side to get the sum on the right. Then we expand using summation identities, and then we use the identities we found out. And now you see there are lots and lots of pesky terms on the left-hand side. What do? We simplify them and get this. Continuing on, we move the terms to the right-hand side to give us 4k cubed is n4 plus 2n cubed plus n squared. Aren't you feeling some deja vu right now? It's because this is exactly the formula for triangular numbers, or the sum of n squared. Isn't that surprising enough? Well, it's about to get more surprising because we're now going to summarize all the results we have. So basically, we have the zero power summation, which is quite straightforward. The first power summation, which you might have learned about in school, and the second and third power summations, which we learned how to derive in here. So pause the video and you would like to write down these results down, and we're now going to talk about more results. Continuing this train of thought with higher powers, well, you can do the expansions and all the algebraic manipulation yourself because the steps are mostly similar for every power. In fact, the procedures are identical, only you have to deal with more complicated equations on the right hand side and more complicated factorizations. If you don't know how to factorize the equation, just use Wolfram Alpha. Computers don't harm you in math, right? There's no rule saying that you can't use computers in math, right? Right? So anyways, with fourth powers and fifth powers, etc., etc., etc. And we have these two results here. Notice that k to the power of 5 has this very simplified look to it, much more simplified than k to the power of 4. Because it's a triangular number squared, multiplied with that pesky quadratic factor, and the denominator is multiplied by 3. And the k to the power of 4 result is actually one of my favorite mathematical formulas of all time. Because there is a nice symmetry in it. 1, 1, 2, 3. And then the leading term of each bracket is 1, 1, 2, 3. And then over 30, which is 2 times 3 times 5. So, I hope you enjoyed this video and see you in another deriving formulas.